Hi everybody, my name is Rajesh Valluri and welcome to my video. This video is part 2 of a two-part series wherein I walk you through the steps involved in using Alexy's YOLO version 4 object detection algorithm. We will be training a custom model with our own dataset. If you are watching this video and have not watched the first one, I strongly urge you to watch the first one before watching this one. The first video deals with collecting training images, pre-processing them, labeling them, and getting them ready for the training process. If you want to do this as a hands-on learning tutorial, you need to first get your hands on some training data. So go ahead and get that part done and come back to this video. If you have already done that and have a bunch of images ready to go, then keep watching. In the last video, we have decided on the classes of objects being detected. I chose to train my model on pictures of birds, but you could have chosen something of your own interest. This could be models of cars, could be different flowers, breeds of dogs, etc. I'm just going to walk you through my dataset, which happens to be a bunch of birds. If you have already collected the image files and created the annotations, your job is 80% done. All that is left now is to get the model trained using those images. We are going to use Google's Colab for this purpose. As I have explained before, Colab is free and comes with generous amounts of compute time for free and offers powerful NVIDIA GPUs. We are also going to utilize Google Drive to hold our training images before we push them to Colab. Because Colab and Google Drive are both Google products and are backed by its high availability and high performance architecture, it's a good idea to use Drive to hold your training images. In addition to the image files and the label files, we need to get the dot names file and the dot data file onto the Google Drive. If you don't remember these two files, just go back to the video or the first video. It's a good idea to zip your images and annotations into one large file so that the transfer is faster between your computer and Google Drive and also between Google Drive and Colab. Please take a look at my Google Drive's folder structure for guidance, as this is important for the next steps we're going to execute on Colab. You can see I have my drive, which is the root of Google Drive, and I have created a folder called birds, and I have my .data file, .names file, and all of the images and annotations zipped together and uploaded into one big file called obj.zip. Before we go into the code, I would like to give you some general tips and tricks in using Colab. If you notice carefully, you can see that I am using the Pro version of Colab. This costs me about $10 a month, $10 US a month, but gives me a little bit more compute power than the free tier would, and it also gives me a bit more leeway on the timeout settings. Other than that, there is nothing much that has material impact on our training process. However, I'll tell you a few things you need to know. Google's Colab, especially the free tier, will have a limited amount of computing power available in a 24-hour period. It will stop training on GPUs after about 10 hours of non-stop training, and you will not be able to start another training session on GPUs until your next 24 hours begin. Ordinarily, your training process will be interrupted and you have to start over, but you don't have to lose the work that's already done. So the code I shared with you will allow you to save your trained models periodically onto Google Drive once every 1,000 iterations. And darknet will allow you to resume training from this point forward. So let's say you have done 10 hours of training and you have two files, like two saved copies of the training weights. So one is at 1,000 iterations and the other one is at 2,000 iterations. And then what you can do is it also writes every few set number of iterations, and that file will be the most recent weights file for you on available to you on Google Drive. So what you could do then is you could use that file when you restart the process as your starting point, and then it means that you have the 10 hours of trained weights available, and then you're actually adding to that. Doing so will actually help you move on. So with any luck, you should get the training done in maybe 2 to 3 days. Um, I believe um, I believe for proof of concept purposes, you don't need any more than 5,000 iterations of training, maybe 6,000. I have used 6,000 though. Right. In addition to this, I have also included a bit of JavaScript, which tricks Colab into thinking you are actively working on the notebook. This way, you can stretch your session to the maximum available length, even though you're not sitting at your laptop and clicking on it, without being timed out by Colab. So this will help you get the full 10 hours or 12 hours. That number is not set in stone, but instead of clicking on it every now and then, if you can kick off the process and go to bed, it'll keep working, and eventually it'll time out, but it'll stretch the session for the longest available time for your account. Now let's take a look at the Jupyter Notebook. The file is pretty self-explanatory, but I have also created headings to explain what's going on in each step. The very first step is to connect to a session and choose the GPU option. You can do this by coming here and you say connect to a hosted runtime, and when you click that, and it'll ask you it's connecting. Maybe because I have already used this notebook, it'll go straight to the GPU session. But what I do is I just make sure by going to runtime and change runtime type, and you can see hardware accelerator is chosen as GPU and runtime shape is chosen as high RAM. In your case, if you're connecting it to Colab for the first time, this will be set to CPU, I mean none, and you need to change that to GPU, and then if available, change this second option to high RAM. Once you're connected to a GPU session, the next few steps are very simple. We need to clone the .NET repository from GitHub, then make changes to the make file to enable GPUs and a few other options, and then compile it. We also need to download the starter weights, which are the pre-trained weights provided by the creator of .NET. We then connect to Google Drive to begin the process of copying across the image files. So let's get started. So like I said, come here. This is the first step where we clone .NET from GitHub. Run this. So this step is cloning .NET into Colab. So that's done. When you see a check mark here, which it means it's done. So go to cd content .NET. So we're in there. Check the file system. So these are all the source files that are shipped with .NET. Now this step changes the directives in the make file for the make command, which means what's happening here is GPU is set to 0, which means .NET compiles by default without a GPU, but now we are telling it to actually use GPU. CUDNN and CUDNN half and OpenCV, these are all various compiler directives, and then we just change them first before we run the compiler. Okay, those are all changed, and then now we just run make. This will compile the .NET application. Takes about a minute or so. So this spinning circle means it that cell is being executed currently, and when you see the green tick mark, yeah, and then that's when it's finished successfully. Beautiful. So it's all good. So we don't need to run this. I just ran this job when I was checking some things, like whether it's actually. So what happened was when I ran this first, there were some errors during the training phase. So I had to come back and make sure that these directives are set properly. You can ignore this step. I mean, there's no harm. It's just displaying this particular line from the make file. Now this step, like I said, we need to download the pre-trained weights. So you're getting it using wget from GitHub, Alexy's GitHub, and this is the starting point, YOLO V4.com.137. There you go, it's done. Beautiful. And then now we connect to Google Drive. in case you haven't done it. If you haven't done this before, it's a little interesting. What it does is, on behalf of Colab, it tries to make a connection to Google Drive, and then Google in on its actually asks for us for our permission, and it gives you a token that you bring to Colab, and then the connection is established. And it's two-way. You can send files to Google Drive, and you can copy files from Google Drive. So this little piece of code does that. And the drive.mount is what's asking us to connect. So in my case, it's already connected because I have done this recently. But what happens is, it opens a separate tab, connection to Google Drive, and then it will give you the code. And then once you can see that on this side, on the left hand side, in the file explorer, you can see the Google Drive connected, but it's actually mounted onto a drive called Drive. And then within that, you can see your My Drive. A big improvement from before, like only let's say 6 months, 8 months ago, was there used to be a space between My and Drive, and that used to drive my code crazy because Unix in Linux and Unix flavors, you cannot have space within your, I mean you can, but when you're writing commands, you have to ensure that those are taken care of. But in this new more recently, Google has changed that, and it's My Drive. And in here you can see this is the folder that I wanted to copy files from. And I can see that, if you remember from earlier, I said there is object.data and object.names and object.zip. So these files are accessible from Google Drive. So that's good. This is all good. So we are cruising along. Now what I want to do next is copy the configuration files, like that object file, which is object.data, which is the actual files, and object.names, which is the names file, which contains the names of classes. And this file, the last file, is a little it's a little different. This depends on, this file depends on what classes we are training and what options we are using and other stuff. So I'll get into a little bit of detail, but just for now, let's run this this cell and get the files across. Okay, good. All the files are copied. Now let's take a break, and we'll delve into this this last file, YOLO V4-object.config. This is basically the configuration file. We need to go into a lot of detail, and I'll explain to you in detail what's happening here in a sec. Okay, one of the most important files, one of the most important configuration files in .NET is the .cfg file. It's called YOLO V4.cfg. It contains, it's basically a file containing all the listing of all the convolutional nets and all the various the networks and the filters used with YOLO V4 configuration file. Perhaps the most critical file in the training process is the configuration file. Alexy, the creator of .NET and YOLO 4, has taken considerable pains in explaining the various parameters in this file. This information is available on his GitHub page, but I have distilled it into simple steps so that you don't get overwhelmed by all the math and the many options in the file. If you look at the file, it's quite complicated actually. It's quite big, and it has a whole bunch of sections, and frankly it's too much information. I mean, if you really want to understand how .NET and YOLO V4 works, yes, this is a good place to actually study. However, just for our proof of concept, there is no point spending a lot of time on this. The crucial things that you need to understand are the number of filters which are in the convolutional network immediately preceding the YOLO section. So there is this YOLO section, it appears 3 times in the file, and immediately preceding the YOLO section is a convolutional network section, And I mean, there's plenty of these, but convolutional nets, but the only things that matter to us are the ones immediately preceding YOLO. So the numbers that are important for us is the filters number and the classes. Obviously the classes are nothing but the number of classes in the training you're trying to train, in the model you're trying to train. So in my case I'm using 5 different birds, which is so hence my classes are 5, and this number is a math equation, which is number of classes plus 5, just stay with me, multiplied by 10. No, multiplied by 3, sorry, number of classes plus the number 5 multiplied by 3, that's it. So don't try to figure out how this number came, this equation came to be. So don't try to overthink it, just use the equation for now. And if you, once you're really familiar with the whole process of training and testing, then spend some time later to understand that equation. So if you want that information, obviously, like I said before, it's all here. So in our case, it's this. You have to change these two numbers in 3 different areas. So if you look search for YOLO on the file, you'll find it in 3 different locations. So every time you come here, you just, so this is the original file. So there is which is trained for Microsoft's Cocoa dataset, which has 80 different classes. So you can see that it's 80. So 80 plus 5 is 85, times 3 is 255. See, so you have to change this number to 5 and this number to 30 in my example, and then you don't save this, but you save it as a different file. Save it as YOLO V4 object.config file. So and once you do that, you upload it back to .NET, to the .NET folder right here. So the steps you have to do is download this file from here, just simple download, and then make the changes, save it as YOLO V4 object.config and then upload the file to this same location. And once you are done, and you are ready to move on to the next steps. So in my case, what I'm going to do is, I have already downloaded the original file, so I come here and I try to upload a file here, and YOLO4 object.cfg, warning message, that's fine, and here we go, along with the other configuration files. So if I come here and just to double check if this is the file I was supposed to be using, and yes, and I scroll all the way to the bottom, there's a YOLO section, classes 5, and the convolutional network immediately preceding that has a filters of 30 filters. Okay, so the configuration file is good to go. Now we can move on to the next steps. Once the configuration file is taken care of, the next thing to do is to unzip the image files on Colab. So the first step is to copy the object.zip file from your Google Drive and all the way to the content folder of Colab. So this line accomplishes that, and once that's done, the next step is to unzip those files. So what we're doing here is unzipping this file and putting them into a folder under .NET folder called .NET data. And again, this is quite straightforward. And once that's done, I already have those files, so I just need to tell, yeah, all those files are overwritten. Then the next thing is, there is this thing called there is a requirement for .NET to work, that it has to have a listing of all the image files in a simple text file. So that text file has to have one line per image file to showing where that file is, where that image file is. It's fairly straightforward. That file is that file itself is mentioned within this file, that in the configuration folder. In the data folder, there is this thing called object.data, and this file has a link to the train.txt, and this is the training images, and this file should have, the train.txt file should have all the a listing of all the image files being used. So we don't have that file, we have to produce that file on the fly. So what we do here is we use this thing called, this little Python script called list_training_files, which I'll provide on LinkedIn, on GitHub, and you can just download it off of GitHub, and then you need to upload it to your Google Drive, like this, like I have done here, like list_training_files, and then from there you need to copy it onto Colab. So that's fairly straightforward. I'll provide you the links for the file, and then you do the rest. So once you copy that file, so this is here, you copy this file, and it's copied, and then you need to execute that file. So that is here. So you go to this .NET folder, the root folder of .NET, and then you just execute it, and then in the same folder as data train.txt, and in the data folder there is this train.txt file, which will show you a listing of all the images. So that's the next step. So once that is also done, you are good to start training. So let's check once everything is in place. So you have, in the data folder, you have object.data, object.names, train.text, those three critical files. And then within the main folder itself, you need to have YOLO V4 object.config. This is the configuration file that we just copied. And if you notice this is the pre-trained weights file that we start our process with. This is provided by Alexy himself, and this is what we use as a starting point. And from that point onwards, the training weights will get updated, and we save those in the backup folder. That backup folder, I'll just walk through that again. It's in the object the data folder. Go to data folder under .NET, and in here object.data, and here you can see that I have given the fully qualified qualified path for where I want the weights files to be saved. So how it works is, you start with the pre-trained weights, and then periodically, once the training begins, periodically .NET saves a copy of the weights, a snapshot of the weights onto this folder, and then eventually after the 6,000 iterations, it becomes the final file. So let me show you, for example, in my case, so any given time you have the last weights, which is in the training process where it is at the snapshot, but then as it progresses through the training process, it writes to these files. Like after 1,000 iterations, it writes a file called 1,000.weights, and after 2,000 iterations, 2,000, 3,000, and so on and so forth. Since we have used 6,000 as a target, the maximum number of iterations, we say we'll see 4,000, 5,000, and then final, and that's the weights file we should be using in after, from that point to actually test or use the model. So we have the object data file already set. We have the the train.txt file ready, we have everything ready, and all we need to do next is to start the training process. So all the files are there, all the image files are there, we are good to go. So let's start the training process. One last thing before we start, remember how we downloaded the pre-trained weights from Alexy's GitHub? So what happens is, when we start training, and obviously Colab is quite generous, you get to train for 10 hours at a stretch, 10 to 12 hours at a stretch, and within those 12 hours you may be able to go through like a quarter of the process, maybe a third, which means you get to have 1000 iterations, 2000 iterations, and then it stops, right? And then in your Google Drive you can see that there is the weights file for the 2000 iteration, and then there is another file for the most latest and greatest, but that's not complete, that's still 2000 plus an incremental value. So what happens is, you don't want to, when you restart the process, you don't want to go all the way back to zero, right? So the good news is you can use that most recent file and then start your training process from there. So what you do is, instead of using this file, which is what Alexy gave us, you can use your most recent file, the last weights file. So this line here is to do that. So so that's why I said don't run this file cell below if you're running the notebook for the very first time, which means you're not copying this. There's nothing to copy for you. The last weights file is not there yet. It will be there eventually, but not yet, just yet. So keep that in mind, and if you're running it for the very first time, you have to run this line. So what it does is, this line, this command is obviously executing .NET, which we have just compiled 15 minutes ago, and then we are using it as a detector. So .NET can operate in multiple modes, but we are only interested in the detector, which is object detection. And then we are not using it to do any inference just yet, we are using it to train. And then here is the key thing, a couple of key things. So we are saying, don't use the default object data file, we use ours, the one we just copied, which is object.data in the data folder, and then use this configuration file. Again, remember, this is the configuration file we have made changes to, and this is obviously the training file, the pre-trained weights file. And don't show means we are asking .NET not to bother with showing us any images just yet. And then you should have noticed this capture line. So this capture line is interesting in the sense that when .NET is executing training or doing anything for the matter, it just spits out hundreds and hundreds of lines with information, error messages, and all of that. So if you're training and if you're training on like a complex model like ours, it will take like 10 hours, 36 hours, and all along it will be spitting out these lines, which we are not gonna look at, but it's going to make the browser clumsy. So to prevent that, we can use this capture directive, but the problem is, if there was actually any error, we won't be able to know. So it's a bit of a balancing act. So what I do is, when I first kick off this process, I actually don't capture it. I just comment out this line, and what it allows me to do is, it just runs a few iterations, so you can see if there is any syntax errors, or if there is any files missing, or any errors that might throw this off. So I let that run for a couple of minutes, and I can tell by the logs lines that if it's either failing or it's working. And if I notice that it's actually working, then what I do is I stop the process, and then I come here, and then I uncomment that line, and then I let it run for as long as it takes. Also, once I know that it's actually running properly, I'll also use the JavaScript I mentioned earlier to keep the session alive for as long as Google allows it to. So Colab allows us to run for 10 to 12 hours at a stretch, but if you're not doing anything on the browser, your timeout will be much earlier. Like you could be timed out in a couple of hours or maybe 3 or 4 hours. So to prevent that, we use this JavaScript which simulates a mouse click. So before we go get that far, let's just see if this is actually working. So we are not capturing the output. We are letting the output display on the browser, and darknet detector, everything in place. So let's kick it off. So yeah, it's working. So there is nothing that screams error to me at this time. So I am reasonably confident that it's working. See, it actually says codes are disabled until the first 3000 iterations are reached. So all of this is working. So what I do is I go back to the cell and I stop it, and I clear this output, and I uncomment that, save it, and I also go get my JavaScript from here. So up from function all the way to the bottom. I did not write this code, by the way. I got it off of the internet, and do a control C. You cannot do you cannot copy using right click. And then let's scroll down. Let's kick off this process, the training process. Yeah, and it's running. You won't see any output here. It's running. And then what I do is I use a little bit of browser client side JavaScript. So press F12 and this screen comes up. This is Firefox, by the way. It's similar with Chrome. And then within this console, just paste the code that we have just copied. Oh, I didn't copy the code properly, JavaScript properly. So let's go up. Control C, console. Yeah. Now if you see this green and a number there, a number in that green font, it's working. So what happens is every 60,000 milliseconds converted to seconds or minutes, I don't know how much that is actually. It just simulates a click on this connect button, which will keep the session alive for as long as Colab allows. So to see if it's actually working, you need to go to your drive, Google Drive, and in my case this is the location. It could be different obviously in your case. So the first things you will notice is object underscore last dot waits. This file will be created like every 45 to 60 minutes, and then if that file is produced, it means it's working, and then you just let it run. You can leave the machine on, and it does its thing. And obviously after 12 hours or so it times out, especially if you are on a non-pro version. And then what you need to do is you have to wait for the full 24 hours to lapse, and then you can start the process again, because you need to use GPUs and whatnot. And when you do that, you have to copy the most recent waits file using this line. Here, using this line, and then start the process again, and then same thing, and you have to switch these two lines. Instead of this line, you have to run this line, this command. But every time you restart this process, especially if you are on non-pro version of Colab, you'll have to do the whole thing, like from the beginning. You have to run all the, you have to download the source code, you have to make changes to the make file, you have to compile and everything, the whole shebang up to this point. And in the here you copy, instead of the 137 file, you copy your own most recent weights, and then you execute this. And it takes a few in my case it took me 2 days, 2 full days, because I'm on a pro account. If you are on non-pro, it might take longer because of the 24-hour restriction. In any case, once it's all done, then you can start testing this model that you have just created. And when I let the training finish, and when I have the final weights, I'll come back and I'll show you how the model is doing. All right, so I have let the training finish, and I have the most recent weights file here, which is object underscore final. So when you see that final, that means the training has completed successfully all the way. So before we do anything with it, I just want to create a simple helper file to just show, display the images, and which is a straightforward Python script. And then what I do is, in my Google Drive, I have a bunch of image files from my backyard, which is under birds, under test images, right? So so I'm going to use the weights to and the model, the train model. So the train model, the command is very similar. So basically you invoke the darknet executable, you using it as a detector, but instead of train you say test, and the rest of them are same. You mention the config file, and then you also mention the weights file, in this case, which is the final weights, and then the absolute path of the file, which is in my case I didn't even copy it to Colab, I just ran it off of Google Drive. So this is Kookaburra, which is this file, Coca1. And if you see this, it's this beautiful Australian bird. It looks like this. It happened to visit my backyard, sitting on my porch. And let's see what the model has to say about this file. And when we run this, it processes the file, and you can see even without the image, oh, not this one, sorry, here, this guy, sorry, not capture the image because I want to see the output. So if you just look at the output without looking at the image itself, you can see that this is the source file, and this is the time it took to predict, and it has predicted with 80% certainty that it's a kookaburra, and it also said the same bird could be a cockatoo at 25% probability. Now let's look at the predictions.jpg file. So every time we run predictions on an image, it gets a predictions.jpg file gets created, which is in the same folder as the main darknet folder. And if you double click it, you can see the output. Okay, so there you go. So it has two bounding boxes, and with the green one is 80%, and it thinks that it's a kookaburra, but it also thinks there is a 25% chance that it's a cockatoo. Cockatoo is another Australian bird which looks very similar to this, not exactly the same, but I mean, they could be mistaken for each other sometimes. And just to make sure that it's working, let's try it on another file. So I also have this another file, 1382. Let's look at that guy. Drive. birds test images 1382, which is image underscore 13 underscore 82, this guy, and that is big file, it's taking a while, and that is here, this beautiful pigeon. I called it pigeon, it could be different, but yeah, I told my model that it's a pigeon. So let's see if it actually detected it. So let's run this guy through the system, through the model. Yes, 88% probability that it's a pigeon and there's nothing else. It only predicted a pigeon. And if you can look at the not this one, let's go to predictions.jpg, which is overwritten this time. Every time we run it, it gets overwritten. There you go, predictions.jpg. There you go, beautiful pigeon, 88%. So looks like the model is doing its job. It's been a good exercise all in all, and hopefully you have reached this point and your success levels are as good as mine. So what's next? So obviously this is a very exciting field, and this is a interesting exercise, but we haven't done anything yet except to prove a point, to prove a concept, right? So I have a few ideas in mind. So one of the things I wanted to do was to create an alert mechanism when a bird of particular kind visits my backyard. I need to get an SMS. Kookaburras are very rare even in Australia, in domestic areas. So when it comes to my house, I want to take a look at it. So I can't be sitting in my backyard waiting for it the whole time. So what I wanted to do was to create a Raspberry Pi based system which scans my backyard every 5 minutes or so, and every time it sees a kookaburra, it actually sends me an SMS or a phone call or a video call or an email or something. So that's the next step, and that's still like a fun project, but it's not really has any practical use to it per se. But what I want to do then is to use this approach to identify, for example, invasive species in Australian forests. So the scientists have certain limitations on observing wildlife, and they would like to know if a species which does not belong in a ecosystem is actually making its way because of climate change or whatever. And that's one thing I wanted to do. And another thing was, I saw a video the other day. There is a foxes which attack chicken coops and eat all the chickens, kill all the chickens. And to prevent that, farmers use dogs, but dogs are living things and they are also prone to failure. But if we can have a camera looking at the perimeter and alerting the farmers when there is a fox or a wild animal that could kill livestock, that's also a good use case for this. So I have some ideas in mind, and I'm gonna try them out, and I'm gonna put them on YouTube as I finish them. But the key thing is, if you have any suggestions or ideas, not just in this particular YOLO based models, but if you have any other machine learning ideas that you would like me to explore or build and then make videos about, please let me know. And if you want to collaborate on any ideas or build any projects in the machine learning, artificial intelligence space, please reach out to me, and I'm very keen to engage with people. So since having said that, I hope you liked the video. I hope you liked my ideas, and please like, subscribe and share this video if you like it. And yeah, please, any feedback is welcomed. And thank you very much for your time. Good luck.